Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, it's August, so therefore it must be IEC month. So we've got 5 Tuesdays in August. That means 5 IEC-related topics that we have been and will be covering. And today's specific topic is all about floating point PID control in Cscape's IEC Editor. Now, we cover PID quite a bit on this channel, and we don't apologize for it. It's a really important tool, a topic that any application engineer needs to be versed in. It's one of the best tools in the toolbox for an application engineer. And we've done several videos on PID. We have a general PID video. We have one that covers more specifically Horner's PID algorithm. We've got one on PID tuning, and those are all applicable to those of you watching today's program. So if you haven't seen those, I'd suggest you go to our website, go to the video search tool, search under PID, and you'll get those 3 plus maybe some additional videos you should check out when you can. But today, specifically, we're going to talk about some of the, specifics on using PID with IEC, and specifically floating point PID with IEC. Now, to talk about a variety of topics, let's bring in our product manager, Mr. Casey Gardner. How are we doing today, Casey?
Hey, not bad. How's it going, Chuck?
It's going good. Now, I don't know if our viewers noticed, but our thumbnail today for today's topic is this cool ice cream truck that Marcy came up with. Don't you love that?
Absolutely.
Now, speaking of ice cream, which is certainly a product that's made, I'm sure, using PID, right? We got temperature control, we got all kinds of stuff going on there. What's your favorite type of ice cream?
I think I'm a little plain. There's not many I don't like, but I tend to gravitate probably towards like a good chocolate chip or Rocky Road maybe.
All right, good. When you said you were a little plain, I thought, uh-oh, here comes vanilla. But hey, I like vanilla.
Hey, me too.
Exactly. I just have to put all kinds of like syrup and other toppings on top of it. Well, my favorite is probably, I have a couple. Mine is either butter pecan or maybe black cherry. Those are definitely 2 of my favorites. Now, getting back to PID, the PID rig, I guess, that I'm using on the bench today is one that our technical support manager, Tim Brandt, built a while back. And you have a story about that rig, don't you, Casey?
Yeah, it's one of the easiest ones that comes to mind whenever PID gets mentioned, or PID application anyway. I still remember it's Tim's story, not mine, but it's a good one anyway in terms of him using it one time. And this rig is really, it's a box with a bulb that you could use, and over time it can heat up a little bit. Well, he was utilizing it one time and happened to have a chocolate chip cookie sitting on top of it, and after a little while it got a little toastier in there. So he remembers going back to that cookie after messing with the application. We're like, man, this is a perfect cookie warmer. It's really what this is. So.
Very good. So we're going to be doing a little bit of cookie warming on the bench, just without the cookie. If I'd have known that ahead of time, I'd have gotten a cookie on there for sure. So anyway, thanks, Casey. So while I'm giving the material, Casey will be answering any questions you have in the chat section today. And if you're watching this on replay, like a lot of you do, give us those comments and questions in the comment section. All right, let's take a look at how we're breaking down today's topic. Okay, we're going to start with a quick review on PID control and the Horner Advanced Ladder PID instruction, because again, the way it operates is perfectly applicable to today's topic. But of course, we're going to spend plenty of time also detailing what you need to know for using PID with our IEC languages, specifically the floating point PID instruction. And we're going to have that benchtop demonstration just without the cookie. All right, here we go. Okay, so what is PID? Well, PID is a mathematical approach to process control, and it was something that's been used for well over 100 years now. And effectively, this mathematical approach involves 3 different parts of a mathematical algorithm: a proportional part, an integral part, and a derivative part. And we'll get into those in a little bit more later. But effectively, this algorithm is probably the most commonly used one for controlling a process, whether that's temperature control, controlling pressure, whatever the case may be. Now, don't get lost in the math equations or the math symbols on this slide, because The most important thing for successful process control is for you to understand your process and how it works. What are you trying to control? What impacts that? All those sorts of things. That's way more important than any specifics or the details on the math equation. Now, let's take a closer look at some of the different elements of a PID algorithm. Okay, so when we're doing process control, there is some sort of process variable we're trying to control. So that's shown in the upper right-hand corner. An example, let's say, is a pizza oven. We'll switch foods this time. Okay, with a pizza oven, we're typically trying to control temperature. So maybe it's 900 degrees, let's say, Fahrenheit, that we're trying to control our pizza oven at. So the 900 degrees would represent the set point for the pizza oven, and the set point is shown there on the far left. Now, what do we use to control temperature in a pizza oven? Well, it depends what type of pizza oven we have. If we have an electric pizza oven, we're probably going to be turning an electric heater on and off. If we have a gas pizza oven, we're probably going to be controlling a proportional valve to let a different amount of gas in to control the temperature. And whatever we're using to control the process variable, that's called the control variable. So our control variable is being effectively manipulated by a controller to impact a process as we measure and try to control the process variable. Now, the specific method we're talking about for control, the specific algorithm, is PID, stands for proportional, integral, and derivative. And the short form on PID is that the proportional term, or the proportional part of the equation, is used to help the process get there fast. So when we turn our pizza oven on and it's only room temperature and we want to get up to 900 as fast as we can, the proportional part of the equation is going to do a bulk of the work to get us to our set point fast. Now, the integral term isn't quite as important, at least in terms of the volume that it impacts on the particular process, but what it does is it basically can help the process get all the way there. So in some processes, by just using proportional, it can be a struggle to get all the way up to the set point. So sometimes integral can really help you get all the way there. And then the derivative term, that one can be used to help reduce overshoot, so we don't go way above our set point when we're trying to get there. And it also can help improve stability. So all the different terms, proportional, integral, and derivative, all have their own role to play in the PID control. Okay, now, Horner has supported PID instructions in their instruction set in Cscape really since almost the very beginning. The first version of the OCS all-in-one controllers was released in the late 90s, and a very, very early version of Cscape included a PID algorithm. Now, the PID algorithm that most of our customers use that's been around the longest is highly effective, and we have two different variations on it. We have an independent algorithm and we have an ISA algorithm. Now, in some of our other videos, we talk about some of the differences, but the bottom line is they're a little different from each other, but either one will work really well in most applications. Now, both of these instructions in our advanced ladder editor utilize integer-based math. And just because PID math is using integer math does not mean it cannot be effective. It's highly effective. Now, every PID algorithm that you use, every PID loop, requires that you allocate to it a 16-word control block. So that's a requirement, a resource required by the PID loop. And if you choose to use auto-tuning with your process, you can also choose either an independent or ISA loop that includes auto-tuning. And when we do auto-tuning with our PID loops, we use the Ziegler-Nichols open loop method. Now, that is probably the most common method that's used, or common algorithm that's used for tuning automatically a PID loop. And we'll talk a little bit more detail about how that works a little bit later. Another feature of our PID instructions is that they can support either a digital control variable. In other words, if you need to turn something on and off rapidly, like a heater, that's a digital control variable. So you can use a digital control variable with our algorithms. You can also use an analog control variable. So that would be in the example of our pizza oven. That would be that proportional valve that opens between 0 and 100% to let in more or less gas, not just an on-off type scenario. So we support both digital and analog control variables with our PID instructions. Now, I talked about the fact that every PID instruction from Horner requires a 16-word control block, and that control block is typically used, at least the first several words of it, are typically used to set up the PID instruction for the details that you need in your application. So it includes things like, how fast do you want to resolve the PID equation. That would be the sample period. Deadbands, upper and lower, how close is close enough above and below your set point. Setting your proportional, integral, and derivative coefficients, that is done as part of the control word as well. And there's additional ones as well, including the upper and the lower clamp. The upper clamp of your CV is the highest value you'll let your control variable go to as you try and control a process, and the CV lower clamp is the lowest value you'll let your control variable get to when you're trying to control a process. And there's several other parameters in there as well, but I pretty much hit the highlights. Now, one of those 16 words is something called a control word, or a config word, I should say, and that is used for setting some additional parameters specifically for things like how is the error term going to operate? Is it the set point minus our process variable or the reverse? Is the output polarity of our process positive or negative? Now, most of the time you can just leave those at their default, but I did want to let you know or point them out that they are there and something to be aware of. Okay, now let's get back to that auto-tuning I talked about. Now, first of all, auto-tuning is not the panacea for every application. As a matter of fact, there are several or plenty of applications where auto-tuning just doesn't work very well, and you'll need to use a manual approach, either to get a better tune or maybe a faster tune or maybe just so it's possible at all. So what is Ziegler-Nichols? Well, Ziegler-Nichols was a pair of scientists that basically discovered or created a series of algorithms back in the 1940s for tuning PID loops. And they came up with an open loop method as well as a closed loop method. And we're using the open loop method here. So basically what happens is when you turn on auto tuning in a Horner OCS PID loop, what it's going to do is it's going to immediately turn the control variable on to its maximum value, which is whatever the value of the CV clamp is. And it's going to turn it all the way up. And it's going to wait, and it's going to do that until you get above the set point. In other words, until the process variable gets above the set point. When that happens, it's going to turn the control variable all the way off until it gets below the set point. And it's going to repeat that process 3 times. Now, while it's been doing that, it's been taking some timings, timing how long certain things have taken. It's also been taking some values. And then at the end, after the end of those 3 cycles, it's going to use the timings and the values that it has gathered, and it's going to plug those into the algorithms you see at the bottom right, and it's going to come up with the first best guess at proportional, integral, and derivative coefficients. So that's what happens if you use the auto-tuning approach in a Horner product with Ziegler-Nichols. Okay, now let's dive into the specifics. Everything I've covered so far is still 100% applicable to IEC. Now we're getting into some of the specifics of using PID with IEC. Okay, so in IEC, you not only have the availability of the integer type loops available, both independent and ISA, but you also have floating point versions of those algorithms. And just like with advanced ladder, you have the ability to use those in auto-tuning mode. So that gives you just more choices altogether. So you can choose an integer-based approach or you can choose a floating point approach, and both can work highly effectively. Okay, let's take a look at one of the floating point PID instructions that's available in Cscape for our controller. So what I have there on the screen is a screenshot in function block diagram. Remember, with IEC, we've got multiple languages to choose from, and with IEC and PID, you can choose between structured text, ladder, or function block diagram. Now, my favorite for me personally is function block diagram for doing process control, and PID would fit within that category. So you can see the instruction there on the screen. There's a number of inputs to that instructions, including the first input is the control block, which remember is an array of 16 integers that is going to be used to set up the PID block. And we'll get to that in a little more detail here in a second. You've also got to plug in your set point, which is a real value. Remember, that's the value we're going to try and control the process variable to. The process variable is also input as a real variable. We've got some inputs that are for manual control. Now, whenever we're doing PID control, we're going to want to leave the PID algorithm effectively always connected to power. Okay, we always want it to be executing. Now, we may want to manually take over control of the process, and when we do that, we don't turn off the PID loop. What we do instead is we put the PID loop into manual mode, all right? And so we've got some variables that we can use, some digital variables we can use to put the controller into manual mode. Also, we have some auto-tune variables as inputs, okay, so that we can kick off auto-tuning and tell when it's done. Actually, tell when it's done is an output. And then there's one more thing that you won't find anywhere else from a PID standpoint in the Horner world, and that is this. There is an input precision variable, which is a real value, in which you specify the input precision that you want to utilize for the floating point values that are part of the algorithm. So a lot of the times a good value to use might be 0.01, for instance. You may want a little more precision, a little less precision, but 0.01 is a good place to start. And generally you're going to enter that in as just a floating point value specifically. Okay, and then the output side, I already mentioned the fact that there's an auto-tune done bit as an output. And then there's also, of course, the control variable, which is a real value, which is, of course, is the output of the PID loop. Now, one thing that's different about using PID with IEC is that you can't directly write to the control block. Instead, there's another instruction that you use to write to the control block, and it is a set PID instruction. And there's a version if you're using an integer version of the PID loop, and there's a version with _R if you're using the floating point version. Okay, so for that particular instruction, you effectively point at the control block, which is tied to the PID that you're looking to set up. And then the parameters are going to be very, very similar to what you see in the advanced ladder setup. You're going to see things like the sample period. How often do you want to resolve the PID algorithm? Your dead bands, your coefficients, your CV upper and lower clamps. A lot of the same ones that you set up for the maybe almost identically the same ones that you set up for advanced ladder, you also have available to set up here with IEC. But of course, the difference is you need to use this set PID instruction in order to write to that control block. Now, one other thing that's a little different with IEC, and that is when you're in manual control. Remember, we talked about the fact that you leave that PID algorithm always on, and then you just take it in and out of manual mode to establish manual control of your control variable if that's what you're looking to do. Well, with IEC, there is another instruction that you would use to actually set the value of the CV manually. So you're going to turn a bit on. That's going to go directly into your PID instruction. That's going to put the loop into manual mode. And then this instruction is going to be used to allow the specific CV to be set manually. So that's another difference we have here with IEC. And in this instruction, just like with a previous one, you do also need to set the precision for the loop. We're going to spend the rest of our time today kind of demonstrating both in Cscape and on the bench how to heat cookies. Well, not exactly. We're going to show you how to set up the PID and IEC. And then, yes, we are going to show off Tim's cookie warming apparatus. Unfortunately, I didn't bring the cookie this time. Now, to kind of understand how Tim has this set up, let's take a look at a block diagram of what we're looking at here. So we're using an XL4, and you'll see it here in a minute on the bench. We're using an XL4 as our controller, and of course it's running a program that was developed in Cscape, and really the core of the program is a PID algorithm. Today we're using function block diagram. You could use ladder, you could use structured text, but in IEC I prefer function block diagram. So the input to our PID, or the process variable, is temperature. So we're controlling temperature. The control variable is effectively a light bulb we're turning on and off to generate heat. And then the output, the control variable output from the PID algorithm in the OCS is actually an analog output, a 4 to 20 milliamp analog output. But there's an external device, a proportional power regulator that Tim has wired in to convert the analog output CV over to a proportional on-off control that can turn the light on and off to control our heat. Okay, and of course the thermocouple detects the heating changes and away we go. That is what our loop looks like. Okay, so let's head over to Cscape and take a look at how we have this set up. Okay, so just like I've mentioned a couple times already, I personally prefer function block diagram when it comes to doing process control with IEC. And you could use ladder, you could use structured text. Those are also available. Okay, so what are we doing here? Well, let's take a look, first of all, where you can find in the toolbox the PID instructions. So we've got two different locations here. We've got PID down here. Those are the integer-based PID instructions. And then we have floating PID down here, and these are the floating point version of the IEC instructions. And I chose to use an independent auto-tuning floating point version. So that would be this guy right here. So that's the particular algorithm that I chose for our example program. So here we have, every time that you drop one of these loops or instructions onto your desktop here, like I did, a few hours ago, you have to give it its own name. Okay, so I named this one temp_loop. So it basically is going to show up in your variable table as a variable for all intents and purposes, and the type of variable is going to be the type of this PID instruction. Okay, so you have to name your instruction, and then it's really a matter of just connecting up the inputs and the outputs for your particular application. And the first thing you have to do when you're talking about PID and a Horner is you need to allocate a control block. So I've got 16 integers. I've got an array of 16 integers called temp loop CB for a control block. Now, one thing that will throw a lot of people off and generate a syntax error is whenever you see an IEC, almost always, whenever you see an input that has these brackets specified, what it's basically telling you generally is don't put the first element of the array as the input. In other words, temp loop CB index 0. Don't put the index 0 part in there, the part that's within brackets. Just put the name of the array variable there and leave that other part off. Otherwise, if you put those brackets in there with a 0 in between, you're going to get a syntax error. So you don't want that. Okay, so we specify our control block as the first input, and then we have a floating point variable as our set point, a floating point variable as our process variable. So again, if we were doing pizza instead of cookies, our set point might end up being 900 degrees, and our process variable would be whatever the temperature of the oven is right now. Okay, we have some manual type inputs here for putting the PID loop into manual mode, and then bumping the CV up and down. So those are allocated here, and then we have some auto tune type variables. So we have a Boolean bit that we're going to turn on when we go into auto tuning mode. And then we have some other settings here for auto-tune. We have a filter setting, we have a responsiveness setting, and we have a type setting, and all these are related to tuning. Now, one thing you'll notice here is there's a hashtag before these particular inputs, which means that what they're looking for here is either a constant or a defines that's tied to a constant. So all these are defines that are available in IEC for the filter settings, the speed of the PID, as well as the type of tuning we're doing. So if we wanted more filtering, there's a higher define with a higher level filtering. If we wanted PID slow instead of fast, if we wanted type PID for our tuning, all those would be defines. There are defines available for all of those, all in the help file. So just go to the help file, search under PID, and when you find the IEC PID instructions, you'll see all the defines there, so you'll know which ones are available to you. Or you can probably just type in constants for those if you wish. In the case of the filter, a value of 0, a constant of 0, a double integer constant of 0 is what correlates to this particular filtering value. But you can find all those details in the help file. Okay, and then of course we've got a bit that turns on when our tune is done, and we've got our control variable, which is a floating point value. Okay, so this is the PID instruction we're using. But as I also mentioned in the slide portion of our program, if you want to communicate or if you want to set your control block, and you'll need to do that for setting up your PID, then you need to have another instruction that's used, a set PID instruction that is used to actually set those values to where you want. So you're basically controlling how this PID algorithm is going to operate. So these are things like, of course, you have to reference the control block. The same control block has to be referenced, of course, so they know that you're talking about the same loop here. We have to set the period. So that's a number in 10 millisecond increments in terms of how often we're going to resolve the PID equation. So in this case, I've set it to 3, which means every 30 milliseconds. You've got deadband settings. I'm not going to use deadband at all. You have your variables that are tied to your proportional, integral, and derivative coefficients. And then you have one that gets probably forgotten the most of all, and that is your CV upper clamp and lower clamp. And the upper clamp is critical in that if that is left at the default of 0, then your control variable will never get above 0, and your PID process will probably never do anything. So Tim would probably hit me over the head if I forgot to mention, don't forget to set your upper clamp on your control variable. And then you've got other parameters in here as well, all available in the help file and all ones that we've more or less talked about in the slides. Okay, so what else do we have going on here? We've got our PID algorithm, we've got our set PID, so we can set the control block the way we want. Well, on the input side of this application, we have a temperature sensor, okay, which let's take a look at our hardware configuration. So this is an XL4 with Model 5 I/O, which means it has a built-in input, that analog input that can be used for, actually has two of them, that can be used for a variety of different things, including thermocouple. So effectively, we're using a thermocouple as our input, and the values are being reported in 1/20th degree C increments. Okay, so that's how our value is coming in, and it's coming in to an analog input register, AI1 in this case. It's coming in as a integer. So if we're going to have a process variable that is in floating point format, and if we want to control our process in degrees Fahrenheit, it's our choice which way we want to do it. If we decide on degrees Fahrenheit, we're going to need a floating point variable in degrees Fahrenheit to be our process variable. So we've got some logic here where we're taking our temperature in, which is just tied to a percent AI, AI1. We're converting it to a real value, and then we're scaling it to get it from 1/20th degrees C over to degrees F, okay? And the easiest way to do that is to use kind of 0 to 100 on the Celsius side and 32 to 212 on the Fahrenheit side. 0 C is where we freeze, 32 F is where we freeze, 100 C is where we boil, 212 F is where we boil. So we can just use that to convert. Now, the reason I didn't use 100 here is because remember, the data is coming in 20th degree 20th degree increments. So a value of 100 degrees C is going to come in our AI register as 2000. 0 C will still come in as 0, of course, but 100 C will come in as 2000. So that's why I've got the scaling set the way they are. So I've got the scaling set here for our process variable. And then down here, I have a little bit more logic that I'll show you before we hit the bench. And that is, this is my manual control. So this bit here, which is temperature manual enable, when that variable turns on, we'll be in manual mode, which means we're going to be manually controlling the CV. Well, to manually control the CV with IEC, we have to use this instruction. So effectively, that's our instruction, so we can manually control the CV. And then, of course, the other part of things is we're going to be doing some scaling on our CV, which is a floating point value, and we need to scale that and convert it to an integer so that we can write it to our analog output value, which is tied to %AQ9. So this is a variable that's tied to AQ9. And what I'm doing here is effectively, I'm taking the raw value from our CV, I'm multiplying it by 20 to kind of expand the range there, okay, to take advantage of more of the range, and then I'm converting it to an integer. But before I do that, I have this binary selection here because the CV, the raw CV value that we need to scale could be coming from our PID loop as an automatic value, or it could be coming from our manual instruction here as well. So I have to select which of the two is being used at any given time based on the fact whether we're in manual mode or not. And I'm going to scale each of those the same way by multiplying by 20 and converting them to a integer. So that's the logic I have here. All right, let's take a look at what things look like on the bench. And one thing I want to be clear on is that I can take absolutely no credit for this PID setup. This is all Tim Brandt's work. So what you're seeing here on the bench is on the left, out of focus a little bit because it's actually taller than the XL4, is a small plastic enclosure with a light bulb in it. And you can see that light bulb is turning on and off. And you may be saying, well, wait a minute, if we're using the heat from the light bulb to control our process and it's turning on and off, how are we using an analog output from our PID to make that happen? Well, that's where we have that separate component that's connected between the 4 to 20 milliamp loop and the light bulb to change that to a proportional on-off control. There's an extra component in there. Okay, now let's take a look at what's going on the face of our XL4. You can see our target set point on the left there is 90 degrees Fahrenheit, and our actual is on the right. So we're holding that pretty darn close, as you can see, within a tenth or so of a degree. which is pretty darn good, and that's especially since it's degrees Fahrenheit. And then I'm showing on the screen my PID algorithms, my coefficients for proportional, integral, and derivative terms, and those look awfully round. I went ahead and did an auto tune, and then I did some tweaking, and I just ended up with some fairly round numbers, and it was close enough for what I was doing, and so that's where I ended up with in terms of my PID tuning. So just a proportional term and an integral term. I didn't need the derivative term because I had plenty of stability and overshoot was not a problem. So I just stuck with the P and the I term. Okay, so what else did I bake into the demo? Well, I have the auto-tuning screen, which if I turn on the auto-tune button, then what will happen is we'll dive into that modified Ziegler-Nichols process. We'll run through the process 3 times up and over the set point. And then the OCS itself will then write the P, I, and D coefficients that were a result of that experiment into the coefficient terms. So that's how that works. And of course, when it's done with that experiment, the done bit will turn on. And then finally, I also have a screen that I can use to manually control the CV. So when I turn that manual mode button from off to on, effectively then I can type in a manual CV that will force the process to go to that specific value, and then the automatic CV will be ignored at that point. Okay, so that is our demo. And we will make this available for all of you to download from our website. Again, the video search tool is a really nice tool that allows you to find whatever you need from a demo program as you're perusing our videos. Okay, let's go ahead and wrap up for the week. So the PID instructions that are available in our IEC editor in Cscape are very similar to those that are available in Advanced Ladder. So I would encourage you to soak up all the PID content you can, and don't worry if you're going to be programming in IEC, but you want to learn more about PID. If a particular video covers Advanced Ladder, you're still going to get a lot out of it. Now, in addition to integer-based PID instructions, one of the nice things about IEC is you also have floating point as an option, and you have to keep in mind that in order to use the PID loops, or to operate them, I should say, there'll be a couple of other instructions to be aware of. One, to manipulate and set up the control block, and another for actually allowing the writing of manual values to the control variable. Okay, so this is the portion of our program when I remind you that we're here every Tuesday at 2 o'clock. Whether we're fully live like we are today, or whether we are pre-recorded and streaming live with someone standing by to answer your questions. All right, this year in 2023, we're celebrating 10 years of the Horner Lighting Group products, so check out their great videos alongside the automation content on the Horner YouTube channel. Don't forget, we have IEC training coming up in mid-September. It's a 2-day course. First time we're having it here in the States. We've had training courses at several of our distributors and overseas, both in Ireland as well as for some of our great distributors like the guys in New Zealand that have been training on IEC for years with the Horner products. So this will be your first opportunity here in the US to come to the factory for IEC training. Don't forget to sign up for that. Okay, next week, we've got structured text math instructions. That's what we'll be covering in a little more detail. We've covered structured text before, of course, but we're going to cover specifically about math next week, so don't forget to join us. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything, and we won't bombard you with all kinds of spam or anything like that. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, when we talk about structured text and math, let's all get out there and do us some good.